Hi everyone, and welcome to another episode of Global AI Notes. Today we'll be talking with Abe Amorokbe, who's a principal program manager at Microsoft for the PostgreSQL database. So, see you in a second. Hi Abe, welcome to the Global AI Notes. How are you doing today?
I'm doing well. Hey, everybody. Good to be here. Good to talk to everybody about AI, Postgres, and hopefully we can learn a lot today.
I guess we can never learn enough about AI, especially with all the changes that are constantly coming up.
That is true. I heard Cohere released a new model like yesterday, and I'm like, every day there's something new to read up about. So it's cool though.
Exactly. As well as good things as negative things, but the negative things we also need to fight against, of course.
Yeah.
Abe, if I need to ask Bing Chat, who is Abe Omorogbe, what would he reply?
Oh, that's a good question. Yeah, I mean that's like who am I? I'm a product manager working right now on the Azure Postgres team at Microsoft. I've been at Microsoft for 4 years, and then I was at Databricks for around a year, and then back at Microsoft again, working really on Postgres. But my whole career has been in AI stuff. I've been working with for a while. Really enjoy talking about it, and just like teaching and talking about the topics.
Okay. We know PostgreSQL, at least most people, as a relational database.
Yeah.
But you will convince us today that we can also use it for AI applications.
That's my goal today. So I love to kind of show folks. Even for me, when I started this team, I was like, "Oh, like what exactly is Postgres?" But knowing getting to know the community, seeing how kind of big and support that's available through Postgres, it's super useful for Gen AI. So we'd love to kind of show folks like what you can do and the extent of what you can do with Postgres and building your app on top of that.
Okay, well, with that, I'm gonna share your screen and I'm gonna give the platform to you.
Sweet, sweet. So yeah, so today we're going to talk about how you can transform your apps with AI and Postgres, and specifically Azure Postgres, because that's the team I'm currently on. So as I just introduced myself, I'm on the Postgres AI team, so everything to do with Postgres and AI at Microsoft, and I have some experience previously working on the Azure AI team as well as Databricks. So today, what I wanted to do to show you how to kind of build this AI application is I'm going to put some context around it, right? So today, we're going to go on a journey to build our AI legal application on Postgres. So what we're doing is we're going to build a legal copilot per se, and I'm going to show you all the steps I took. So first, talk about why Postgres. Then I'll talk about how I ingested the data from the US, how the team ingested data from the US case law data set. We'll talk about how we do semantic search, basically, which is vector search, super important for AI applications. Then we talk about what exactly RAG is and how it integrates with Postgres. Talk about some common problems of RAG and how Postgres addresses those, and then talk through some advanced RAG architectures and how we can increase accuracy and things along those lines. So just to quickly get started, why Postgres? Why exactly would I even want to use Postgres for this? So realistically, here are just a laundry list of stuff Postgres offers out of the box, just right in the database. So especially if you're using the Azure Postgres offering, right off the bat, you get things like right away AI model integration. So right in your database, you can do some AI commands. I'll show you how that works. So things like embeddings right inside your database. You can do vector search inside the database. So you have vector search and a vector store in Postgres through PG Vector. It even supports unstructured data. So you can save JSON blobs right inside Postgres. So it's not only structured, so you can store unstructured content in there as well. And then it supports graph databases. So we have another extension that can support graph in Postgres itself. And then you have geospatial data support as well. So if you're building an app with maps and things along those lines, all that data can be stored and used just directly in Postgres. And then not to talk about like extensive OSS support. So probably every GenAI framework out there supports some sort of Postgres plugin. So it's super nice to like plug that in and use Postgres for these applications, as well as the super vibrant community and support. So if I've run into any issues, there's usually somebody that's using Postgres that can help that. And to speak to that, at the bottom there, you can see that Postgres is the #1 developer database according to Stack Overflow. So I think over 50% of developers, professional developers, pick Postgres as their database of choice. So if you're already doing app development and you're already using Postgres, why not flip over and build your GenAI app on this as well? So going into the basically meat and potatoes of this is, as we kind of build out this legal AI app, first thing we want to do is ingest data. And like, how do we do that at Postgres? So like, just to kind of give everybody context, right? What we're doing is we're going to build kind of this legal research copilot app. And the idea is like, if you are kind of like a legal researcher, or a lawyer in the state of Washington, there are a bunch of cases that you could read and you could help defend your clients. So what we're going to help build is we're going to help you build some sort of app that can help you defend your clients against, like landlord and tenant issues. So basically an issue would be like, hey, there's the water leaking from the apartment above me. What exactly can I do? And then you type that into this legal copilot. And as a lawyer, I can help you answer that question. So we're going to go ahead and show you the steps to build that out. So the very first thing we're going to do is like, what we did as a team is we looked at kind of the legal data set of Washington State. So what the government or this initiative case.law, they have brought in and scanned all the legal cases all of US, and we focused in directly on Washington. So around 100,000 cases, around 600,000 pages scanned. And we're going to take some of that data and put it into Postgres and see if we can do a search on that and give you better results for your GenAI application. So very, very high level, the way this works is we looked at the US case law data set. And what we just did is we went about and we downloaded all the JSON files. So these JSON files have the case data in them. So what we did is, the good part you can do is you can pull in that metadata, you can pull in the case law data and save it directly in Postgres. So on the right, what you see is inside Postgres itself, we created a table that represents all the cases. And the table has 2 columns, the ID for the case and just the unstructured data. So the JSON blob with everything to do with that case. And then because it's all saved in Postgres, what we can do is we can do further kind of manipulations on top of that. And as you can see, it's a simple Python script that goes in, talks to Postgres here. We fetch the JSON data from the case law data set, and then we store that directly in Postgres. So high level, that's how we get the data, and that's how we start doing things like searching. So then the next step here is, okay, now we have the data. We kind of want to start building now. Okay, what exactly is this copilot going to do? How can Postgres help me further in building out this app and being the kind of data storage for this app? So the very second thing is, okay, how does search work? And how can we use Postgres to get better search? So now after that, there are common approaches to searches. You can search through patterns, like with I like. You can search with full text search. So you search through a phrase, and then you can search with vectors. So I'm going to walk through each of these and these are all supported with Postgres and kind of show you why we picked what we picked for this specific use case and how Postgres supports all of them. The very first choice is using I like. So for example, if what we wanted to do is like, hey, we want to find, properties with water leaking above, with I like statements, it's best to kind of use a word. So, these approaches are a bit too simple and pretty limited because the results I'll get to be a bit too much for it to be context to my, application. So, I'm going to get either inaccurate results or it's not going to find me any results for very complex phases. So that approach may not work. So if I were to have a whole sentence like, water leaking from an apartment above, because there are no cases with that in the past, I'll probably get 0 results. So the second thing a lot of folks try is like, okay, let me try a full text search, like a full phrase search. So, hey, how can it match on this phrase specifically? So again, we can try that again. We get a little bit of better results if we search like, hey, water leaking from the apartment above. We do a full text search. but that's not as efficient as, let's say, using vectors or things like that. So it struggles with nuanced queries. So the last option, like that or another good option in Postgres itself, is Postgres also has implemented vectors. So like directly inside Postgres, we can actually do a vector search. So I'm going to touch on what exactly vector search is and how it works. But one key difference here to all these searching approaches is you would notice these are all using where clauses, while for the vector search, we're using order by. Because what it's doing, it's ordering by, hey, give me results that are closest related to this water leaking from the apartment above. So before we kind of try and understand then why we picked vector search and how it works inside Postgres, just want to do a very, very quick overview on what exactly vectors are and how they work in this. So very, very quick high level is, vectors are just a representation, a number representation of a word or a sentence or a phrase. So for example, as you can see there, if there was a word dog and a word cat, both of them, let's say they just represented with a bunch of dimensions, both of those will stay around the same space, around the same area in vector space. So when I do a query on that and I say, hey, can you order by any points that are close to my search dog, it will kind of give me words related to dog, and then cat could fall in that. So very, very high level, that's kind of how vectors work and how vector search is going to be implemented, inside Postgres. So before we can even do that search, we need to somehow convert that word to some sort of vectors or numbers. So there are many models to do that. So a very, very high level model to do that is word to vec. This is super common in the NLP space, but not the most powerful model, but just give you a high level. Take a word like dog and you can see the vector representation. And then there are a bunch of other models here you can see that do the same thing. So most folks are going to use OpenAI Text Embedding 3. That's what we use. But there are other kind of different embedded models out there. But it'll take any word or any phrase and it will kind of embed that into a bunch of different dimensions. So this 256 to all the way to 3,000 dimensions. So yeah, very high level. What that'll help you do is it will take all those words, it will map it in a graph, and it can make us do similarity search a little bit easier. So as I talked about, I like was patterns, full text search was phrases, and this is kind of giving you more of like relative similarity of what I search. So very high level, that's kind of how it works. And I'll just want to quickly show folks and like, hey, like if there's a word like just say food, for example, right? And this is what I'm showing on the screen is a very, very easy to use website on how we can, show vectors and what happens. So if I were to search the word food and see, okay, how does this get turned into a vector? So for example, if I was using the OpenAI model, the same food vector, these are the top 10 most similar things to food: eat, stuff, live in, life, fish. So things along those lines. So if I were to do a vector search on my AI application, these are the top 10 things that will return if I were to search that word. So like having that kind of intuition kind of shows you how we can use these kind of vector searches inside Postgres to kind of further the results of kind of these GenAI applications. So just to kind of put it all together, like why exactly is this important? So especially in this AI world, where vectors come in is, so in this case law data set, what we're doing is we're turning raw data, we're feeding into that deep learning embedded model, we're getting some vectors back, and with those vectors we can now do a similarity search, and that could power things like recommendations, it could power question answering applications, and it could also power RAG applications. And we're going to walk through how we can do that today in Postgres. So with that being said, there are a few things you need to kind of create these embeddings and create these vectors. And because Postgres supports a bunch of different extensions, so Postgres itself has some extensions you can install right in a database. One big one we use a lot on this team is the Azure OpenAI extension. So basically what that is inside Postgres itself, we have an extension that can call out to OpenAI, AI language services, the AI translator, or Azure machine learning. And that can really help us, supercharge some of these processes on the data on the database directly. So give you like a very, very practical idea. So basically what this would now look like in our use case is when we do get all those cases, they have been loaded into our vector database. What we can then do is basically what I'm doing here is I'm taking that case table, I'm creating a new column for all the vectors, and then I have this Azure OpenAI extension where I can create the embeddings with the embedding model, like I said, and then I can store all those vectors. Those will pin the cases and the vector representation of those cases for each case. So this is what it'll look like in database. So we can do a similarity search on top of that. So like super high level, this is what it'll look like. So I can do like a select star from. So let's say I'm in PG admin. You can see here, if I were to just run that exact same thing, I would get a bunch of cases. So what I'm doing is, hey, I'm going to do a vector search on water leaking from the apartment above. And then you can see right there, I'm getting, some results that are similar to what I'm asking. So you can see it talks about leakage and water. So right from Postgres, I can start doing these vector searches and getting the right results to kind of power my application. So now that we're kind of on the same page on vector search and semantic search, how can I now take this and incorporate it into my applications using Postgres as kind of like the backend for all of this? So that's where we kind of go in and touch on, like what exactly is RAG and how does RAG work? Just the basics and how we can use Postgres to improve our applications. So super high level, I'm going to kind of skim through this mainly because, the general basics of RAG is you have data, you can do things like chunking, you can embed it and then put those embeddings in Postgres like I just showed you. And then you can go ahead, take a user query, that query gets, vectorized through OpenAI, and then you try and match all the data, you retrieve all the context from the users, and then from that context in the question, you send it to OpenAI and you try and get a response. And the most important part here is this information retrieval is kind of where Postgres shines. So all that data I showed you got chunked and vectorized, saved in Postgres, and that's how context can be retrieved to kind of back your RAG applications directly from Postgres. So how does that work? The very, very high level basics, and this is just some VS Code screen on the right that I'm showing is, first things first, we're in Python. All I'm going to do is, connect to my database. I'm going to do that same query I just showed you to retrieve the context. After I retrieve that context, so I got, get me the top 10 cases that are related to, and then S just being water leaking from the apartment above. I get all the context for that. And then from that data from Postgres, I can plug that right into my my OpenAI message. So you can see here, I'm going to put, hey, you're an AI assistant, answer from this context. So I put the context in here, I put the question, and I send that to OpenAI, and I get the response. So context from Postgres, send a response to OpenAI, and I get a response and send it back to my user. So super basic on how we can start using Postgres as the context generator for a lot of these questions. We can get the question, we can do a similarity search, get all the relevant content to answer that question, and then send it to the LLM to answer. So very high level, how does that work and what does that manifest? How does that manifest itself inside this kind of legal Copilot app? So what you're seeing here is kind of a more cleaned up version of this application. So what we can have is we can kind of ask the very similar question of, hey, water leaking from the apartment above, what are the legal precedents of this case? So like most chatbots, what it's going to do is going to send the question, is going to take the context, and it's going to try and answer that question. So as you can see here, what we're able to do is, this is all backed by Postgres. So what we're able to do is answer that same question, and you can see it has references to some cases that are specifically related to what I have saved in my Postgres database. And so like that's kind of like high level of how these things work, and how Postgres can really help you do the very first thing of like, basic RAG, and then do some similarity search on your data specifically. And then if I were to ask different questions, it would say, hey, I can't answer this. It has to be documents based on this case data. So that's kind of high level how it all works. But now the big thing here is for that information retrieval pipeline, what we find a lot with customers is there are two big problems that we always see. So the first one being scale. So what happens when, hey, I don't just have 10 toy rows, I have tens of millions of rows. What happens there? How fast is the search? Can Postgres handle that scale? The quick answer is yes, it can, but you just kind of have to structure it and architect it the correct way. The second big problem is accuracy. Hey, like we just kind of did a vector search here. How do I improve the accuracy to make sure that the result I'm getting actually answers the question properly? I want to have the right context to answer this question properly. So what I'm going to go over is like how we solve problem one with Postgres and what are solutions to solve problem two as well with Postgres. So solving this very first problem of scale, the thing we try and implement with folks is kind of vector indexing. So super high level, there are two very popular vector indexes today that work directly in Postgres. One is IVF flat, and then the second one is HNSW. IVF flat is more of like a clustering algorithm, super memory efficient, but it needs a lot of memory to work well. And then same thing with HNSW as well. But HNSW is a multi-layered graph structure that the graph is updated incrementally over time, but it's a little bit more like accurate and a bit more efficient when you're trying to find data on biggest sets of data, of data. So kind of generally speaking, right? Like which do you pick when if you want to kind of speed up these searches at scale? When you use an IVF flat, like generally we recommend that, hey, if you're working on a large data set with super, small dimensions, perhaps IVF flat is your best option here. But generally speaking, like if you're doing smaller data sets with super high dimensionality, HNSW will work super well for that. But then what happens when you have kind of larger data sets with high dimensionality? Like how can we solve this problem? What's the best thing to use? So just a quick divergence here is we'll introduce this concept of disk ANN. So, and specifically on the Azure platform, and some other startups have this as well, but Microsoft specifically has developed a vector search algorithm called disk ANN that's super performant for those scenarios. So basically what happens is disk ANN generally, what it'll do is it'll create that similar graph-like index inside memory to speed up kind of any of these vector searches. But what it'll do is it'll compress and save all this, all the graph, will compress the representation of a graph in memory. So you can have a very reduced, memory footprint of all these vectors. And then on disk, it would save kind of the full representation of your vectors. So when you do a search, it would, hey, find everything that's like all the closest vectors to your search in memory. So do a super fast search. And then after, what it'll do is it'll compare and re-rank those search based on, hey, this is the actual full representation of that same vector on the SSD and give you a better result. So kind of why that's important is one, at scale, you get super fast speeds on your results back on million row data sets. And then you also get that additional accuracy because it will compare against the full vectors that are on disk. So that's kind of like high level how we solve that kind of scale problem. And yeah, with this index, it's fairly easy to use, like most indexes. Just create an index in disk ANN, and then you can do a faster search. So, after we kind of talked about that and talked about kind of, hey, these are why I use Postgres, why I should use vector search, and how vector search can help my RAG applications. some common problems to solve, the problem of scale. The second thing is like, how do we solve that second problem with advanced architectures? So the second big problem we always hear is accuracy, and that's super relevant in the industry today. And there are a few advanced architectures that we can implement directly in Postgres to kind of help folks increase the accuracy of the applications. So on the left side, you see in basic RAG, there are a few things you can do to improve your RAG application. So you can improve your chunking strategy. You can do things like, hybrid search. You can do things like better metadata filtering. But that's just, one approach. So if you were to kind of implement some advanced architectures, there are two we're going to talk about today and how we can use them in Postgres. You can do semantic re-ranking, or you can implement a knowledge graph with GraphRAG to improve those accuracies. So the very first thing I'm going to touch on is, okay, how exactly would you use something like a semantic re-ranker for, improving these accuracies? The way it works is you do that vector search we talked about. And then rather than just getting top 10, what we'll do is we'll do a vector search and get the top 50. After we get the top 50, what we'll do is we'll take that same query and compare it against every single entry in the top 50 search. But rather than comparing the vector similarities, what we'll do is we'll actually re-rank and compare like the semantic meaning. So high level, let's say one thing says water leaking and water leaking from apartment above, but the top search says like water leaking from the river, right? Those semantically may not be very similar, so that gets re-ranked to the bottom. And then something that talks about water and apartment might get re-ranked to the top because semantically that's a little bit more similar than even if the other result had water and leaks in it. In the vector representation, they might be the same, but semantically, because one thing is talking about river, the other thing is actually talking about a house, it would be re-ranked. And then you get, the top 10 most relevant results back. So in Postgres, how that gets implemented is, you can write a query in Postgres and call it from Python. And then what you would do is you would kind of call this kind of semantic relevance function. And that's created by, we have specific code in Azure Postgres in our solution accelerator that you can call this semantic relevance query. You put in the exact query you're using, the amount of results you want, and then it will re-rank the vector results based on the semantic relevance. So I'll quickly show that as well and what that looks like and how that changes results. So you can see right here, we have the vector search results. If I were to show you here, you can see the recall here is sitting around 40%. So what you're seeing is these green are what was returned by my vector databases, by my vector database. So these are 10 results returned by my vector database, but the gold is the one it should have returned back. So if I were to clear this and pick semantic re-rank and do the exact same search, so we're going to see like if this kind of improved results, and if we're retrieving some things are maybe a little bit more accurate. So again, it's kind of giving me a result. You can pause here and I can read the results, but I'm going to go right over to see, hey, has the relevancies improved? So these golden data sets are from us. We checked ourselves to see what would give us the best answer for this answer. And you can see here that relevancy increases, the accuracy increases a tiny bit using the kind of re-ranker. So that's one speed up there. And then this is available. Take a screenshot here of we have some accelerators here where you can go ahead and use a re-ranker. So you can see it uses Postgres, it talks to Azure Machine Learning where the model is, and then it gives the result back to Postgres. The second big approach here is GraphRAG, like I explained before. So the way GraphRAG works is it takes that same data, that case data, it extracts kind of the entities from that data. So it extracts all the connections, and then from those connections, it creates kind of like a graph query that you can use to give you more accurate results. So basically the way we did it today is what we did is we created a graph based on the cases, and we connected all these cases together to say, hey, look, if the cases are more relevant, if it has been referred to by more cases. So in law, you can have a case and it has a bunch of references to it. So we kind of created a graph to represent those sort of cases, and then we kind of skipped the entity summarization part. And then what we were able to do is we create a graph query to kind of ask our Postgres database, hey, can you give me all the cases that are fairly similar to this vector search, but also have a high number of other cases referring to them. So we're able to represent that as a graph and kind of give more accurate results. So very similar to, if you've ever used any sort of knowledge or graph database before, what we're able to do is improve these results by creating this graph query. So we're able to create a graph query with OpenCipher. So basically what you're seeing here is we're taking the nodes on the graph, any kind of node, match any nodes that are related to other nodes, count all the relations for all these nodes, and kind of give me back, whichever ranks the highest. Whichever one has the most references to is probably the most relevant documents I should be using. So very high level, I'm just going to quickly go over, what that will look like with GraphRAG. So last search we're doing here is we're going to try and do that same search with GraphRAG. I'm just going to skip right over to where it's kind of producing those results. And we kind of see the results move up from 60% to 70%, because with GraphRAG, we're actually hitting the results, as you can see here, to have more references. And the more references they have, it's kind of better results for our application. So like super high level, that's all kind of supported with our Apache Age extension. And then you can kind of read more about that with our kind of solution accelerator. If you check that out on GitHub, so it kind of shows you how we take the data, we kind of create a GraphRAG solution, store that whole graph in Postgres, and return better results for your application. So super, super high level. I know I'm just literally, I think, just a little bit over on time, but just wanted to kind of hammer home the point that, just in these slides alone, I showed you how Postgres can support a whole bunch of things to help you with your GenAI applications. Things from, vector search, GraphRAG, semantic re-ranking, storing unstructured data, storing vectors, and integrating with, a bunch of other extensions in the ecosystem. As you can see here, like if you're using, a managed service like Azure, you can get things like scaling out, compliance, and things that could really help you scale out not only Postgres itself, but scale out your application and support more use cases. So that's kind of it for me. That's kind of it for this presentation, and kind of giving you a good idea of how you can use Postgres plus Python to create kind of, or another program in which to create your RAG and GenAI application.
Great, thank you for this introduction, Abe. I think it was quite useful since it's also quite new. But a question that probably many people have is like, we have Cosmos DB, we have Azure AI Search, we have PostgreSQL as vector database. We can still run many other different things on the Azure platform. When do we choose what?
Yeah, I mean, like for me, I think the answer for me it's fairly simple in my head, maybe because I'm working on the team. But I think when you're kind of looking through all these databases, it's like, what exactly are your needs? So we know some customers really like using unstructured databases and want to kind of, hey, we have a lot of unstructured data coming in, even though even though Postgres does support that. Like, if you're already using unstructured database, it probably makes sense for you to stay in Cosmos, what you're already doing before. So that's what we'll recommend. If you're using a structured database and you're already like fully integrated inside the Microsoft architecture, and you've already used things like SQL Server also supports vectors as well, so you can stay in SQL. However, if you want you're using you want a structured database, you want a lot of flexibility, and you're implementing a lot of stuff with open source software, right? Postgres makes the most sense there because Postgres is fully open source. It's super flexible. You can add extensions. There's a kind of big community around it. And all you want is like, hey, look, I like my open source setup. I don't kind of want any lock in here. I want to, build it all in-house, and then I just want to manage it in Azure. Postgres probably makes the most sense there because the code you write for Postgres would work on Azure and work on anywhere. So it really depends how you're structuring your enterprise here, or like your application. But I'll say there are a lot of choices out there. It could all be done well, but Postgres is top database right now for developers, one of the top open source databases, and it's supported by a lot of open source frameworks, especially as GenAI moves super quickly.
Okay. Does that mean that these elements that you just showed us today are also available on Postgres that is not on Azure?
No, all these elements I showed you, they are all on Azure Postgres. So everything I showed you, they are on Azure Postgres specifically. Yeah.
Okay. All right. Okay. Cool. Well, Abe, thank you very much for your presentation, for explaining us how we should also make use of Postgres for our vector database. Next week, we will also have another session where we will be talking about how contextual data transform language models. Also going to be quite interesting. So please join us as well. Abe, we wish you all the best with your work further on Postgres, and looking forward to any more new stuff that is coming, maybe during build, who will tell us.
Sweet. Yeah, no, I didn't spoil any surprises, so hopefully build in May would be pretty good. You guys would see a lot of the new stuff, we're coming out with. And yeah, no, we'd love to show folks more if they're interested. But yeah, thank you for having me, and the links are in the chat or in the comments.
Yeah,
so
of course, yes. In the chat already, so anyone can just copy them from there.
Sweet.
All right, cool.
Sweet.
Thank you very much, everyone, for watching, and hope to see you next week. Bye-bye.
Awesome, everybody. All right, bye.